Okay, hello everybody. Thank you for coming. So let me first thank the organizers for having me here. So it's really a great pleasure to be at the Institute and to have the opportunity to present my work today. So I will speak on mean field theory for inhomogeneous networks. And this talk is based on ongoing work I'm doing with my PhD supervisor, Claudia Krüppelberg, who is also in the audience. And first I will present the agenda for today. So I will first review some classical mean field theory for those of you who are not so familiar with this topic. Then I will discuss some shortcomings of the classical mean field theory, and then provide a mean field theory for inhomogeneous networks, which is the main part of this talk, and I will finish the talk by giving some concluding remarks. Okay, so what is mean field theory about? So it's a concept which has been used in physics quite often. So in physics, you typically have a large system of particles which interact with each other. And this system is usually complex because there are many influences from each other, but the typical influence of one particle on another particle is small. And the idea is, of course, now, okay, so you have many, many small influences, maybe you can average them out. Yeah? So that's the idea of mean field theory. You try to approximate the individual behavior of each single particle, which is small, by the average of it. Okay? And this gives you the opportunity to reduce a many-body problem, because you have a large system, to the investigation of a single one, because the other ones will only affect it through an average. Yeah? So that's the idea. And mean field theory has not only been applied in physics, but also in other disciplines such as biology or economics, as I will come to it later. So I think the best thing we do now is we start with a simple example to explore the main ideas behind this concept. So I will have n agents. You can think them of as particles in physics or banks in finance, if you like, whatever. I'm labeling them through 1 to n. And each agent has a stochastic process associated to it, which I call xi. And each xi is driven by a Brownian motion. For simplicity, at the moment, I assume they all are ID, okay? And now I will specify the mutual interaction. So given a particle I, how is it influenced by another one, say j? I assume that the interaction between the particles are all homogeneous at the moment, meaning that j will influence I by a constant rate. It's this one, and I assume that the rate is proportional to 1 over the number of agents. This gives you, if you put this into an SDE, the following simple model. So it's an Ornstein-Uhlenbeck type process. The evolution of particle I depends on the state of the other ones, because they act on I through this rate here. And this tells you what I gives out to the others. So this is what comes into I, this is what goes out from I to the others. And you have, of course, your noise here. Okay, so this is the model, and what does mean field limit mean? So mean field limit means you consider the limit when the number of agents goes to infinity. Here, capital N. Well, what typically happens? So I first have some applications. So okay, let's first discuss the applications, then the limit. So as I have said, in physics, people use it to model the interacting behavior of particles, like in a sample of gas, for instance. People have also used it in economics to model the wealth of agents, which interact through trading. This is the Bouchot-Messard model from 2000. It has also been used by biologists to model the flocking behavior of birds. So it's a big swarm, and what happens with the interaction. And also, Vogt and Sun have used this model for modeling the lending and borrowing behavior of banks. And I know that some of you in the audience aren't that keen of this model, but still this is what they are doing. And as we also have heard in this seminar or workshop, is that many people use these kinds of models to model statistically dependent processes. So this mechanism here does not necessarily need to explain the internal mechanism how J affects I, but maybe only what you observe. So the statistical observations you made, for instance, through a correlation analysis or something like this. So it is also useful in this respect to think of them as a statistical model, okay? But now, what I wanted to show before, so the limit. So what happens if the number of agents goes to infinity? So, well, you have here a weighted average of the individuals. Well, the law of large number will tell you that this probably goes to this one. And indeed, if you compare the two systems, the only difference is that you take the average here. And this gives you the simplification you want, because in this limit model, all the xi bars are decoupled. They no longer are no longer dependent, but are independent of each other, because the others only enter through an expectation. This gives you the possibility to reduce the dependent structure to an independent system, yeah? So which is the advantage of taking mean field limits. And this is also what people call propagation of chaos, because typically you will assume that the starting positions of your processes will be independent. In the original system, the dependence will be destroyed instantly, because as soon as time sets on, your process will interact and they're dependent. However, in the limit system, they stay independent, yeah, as we can see here. This is what people call propagation of chaos, chaos meaning independence.
Well, they don't stay independent. I mean, that's what
you approximate them through a system of independent things.
But they don't stay independent. That's not exactly what it says. It says that if you have n particles and you fix k finite, n goes to infinity, then if you look at the joint distribution of the first k particles, that will converge in log to a product distribution.
Yes,
but
yes.
It's important that k is finite and n goes to infinity. So if you follow two particles in the gas in this room, they look like they're independent. But if you look at all the
of course, yeah. So you're looking at the finite number of things because you
finite.
Only have a finite, yeah. So yeah, that's true. Yeah, thank you very much. Yeah. So this is the precise version of the statement. So here I'm looking at only at a univariate distribution. You can also extend it, as Rama said, to joint distribution of a fixed number of particles. So if I look at the ith agent and look at the difference, the supremum of the difference between two processes up to a time capital T, this will have an expectation which decreases with order square root of n. Yeah, so this tells you that if n goes to infinity for one or for a finite collection of particles, you can approximate the behavior by the limit system.
But for example, if you look at the order statistics,
it
doesn't behave like order statistics of n dependent.
Yeah. So it's really just the single or finitely many number of particles. Okay. So of course there are some criticisms you have to make here, because in this model all agents are assumed to be statistically equal. So everybody is driven by the same Brownian or a Brownian motion with the same distribution, all interact with each other at the same rate, all driving noises are independent. Such assumptions are maybe reasonable in particle physics, because there, if you have a molecule or if you have many molecules, they will be of the same type if you have one sample of gas. But in finance or economics, where you do have very different kinds of players, it's no longer reasonable to assume that the particles are statistically equal or interact with each other in the same way. So that's the main motivation for our work. So we want to extend this mean field theory to a number of agents who interact with each other in a different way. So from one pair to another pair, it should be different. Okay? So this is what we want to incorporate in our model. So we want to have different types of agent. For instance, you have a core and you have a periphery. You have the influence of the cores. This doesn't vanish typically, because if you have just a finite number of core banks, their influence on the other ones will remain strong even if the number of banks goes or agents goes to infinity. And we only want that the influence of a periphery agent becomes smaller, like 1 over n, let's say, not the influence of the core bank. And at the same time, we also do not want the number of core agents to go to infinity, because in the classical mean field theory, you have that the number of all particles goes to infinity. And here, we only want that the number of periphery, that this goes to infinity, but not the number of core agents. And of course, the weights are allowed to be different from pair to pair. And this is another point we want to incorporate, that noises are allowed to be dependent. Okay? Which gives us the following model. So we replace the constant weights by a matrix, Aij. So Aij gives the influence of J on I. And the noises here are no longer independent. Yeah, so you can think, so the noises I will take in this talk as Levy processes. You can also think of them of Brownian motions if you want. So it depends on what you want. And but still, this model here is a linear model. So the influence of J on I is still in a linear way. At the end of the presentation, I will give you an extension to nonlinear functionals. Okay, so. But first of all, we start with a simple case where you have here matrix. Okay, so the mathematical implementation is as follows. So I have here the covariance matrix of the noises. Okay, it's sigma. And now here comes the definition of what I mean by core and periphery. So for each agent I determine a number of other agents which are important for this particular agent. These other agents are called C of I, so the core agents for I. And similarly, the P of I designates those who are not so important for I. So in particular, the definition of what is core and what is periphery does not need to be the same for everybody, but may depend on the agent. Okay, so you can of course also fix a fixed set of cores and a fixed set of periphery, of course. Okay. Accordingly, I will partition the matrix into a core matrix and a periphery matrix. So the core matrix, I put everything 0 where it's the periphery is influenced, and the periphery matrix, I put everything where 0 where it's the core. Okay, so it's quite simple. Here an example. So I have here a fixed core, so 1 and 2. In a fixed periphery, 3, 4, 5. So this may be an interaction matrix, and I decompose it into these two parts. So core means the influence of the core onto everybody. This is important. So that's the reason why I keep them into the core matrix. Why I put into the periphery matrix the influence of the periphery on everybody else. Yeah, so, but this distinction is up to you, so you can choose it. And okay. Yeah.
It will come back.
It will come back?
Yes, something happens.
Oh yeah, it's coming. Sorry.
But it's,
And we're at the main result.
but it's somewhere. Okay, here. As I have said, this distinction between core and periphery is up to you. And for instance, if you look at the numbers, and for instance, this is just a very small number, and you can also put it into here if you want. Okay. So it's up to you, but this will of course reflect the results after all. Okay, so how does the mean field look like now in the heterogeneous system? So this is our original system, and this is the mean field system. Let me explain. So, of course, if you have a core, and you assume that the core's influence on the other ones are strong, then you cannot average them out. I mean, it would just be an error to make it, okay? So this is the reason why we keep the core's influence still present in the limit. And what we do is we average over the periphery. So this is what we want to average out. And the noise is, of course, the same. This gives you the following phenomenon. So in the limit system, what you still have is the full dependent structure of the core. So you have to be able to get hands on the core. If you cannot manage them, then you have no chance, because they are dependent as they are, and you cannot make simplifications. But the influence of the periphery on the core, this you can simplify through the limit model. And in the same way, if you are in the limit model, how do the peripheries depend on each other? Well, they only depend on each other through the core. So the peripheries' behavior is completely determined by the core and its own noise, and no longer a steer from each other. So that's the idea. So what you really average out here is the influence of a periphery bank, not the influence of the core.
Is the core infinite?
You can, but typically not. Typically not.
It seems to indicate that it's possible.
It's possible. If the core is infinite, you will typically assume, as in McKean's example, that also the single influence of a core goes to zero. Then you should think about taking no core at all. Okay? So you do this only if the number of cores is somehow finite and the interaction remains strong throughout the number of particles. Okay? Yes, so I want to prove a law of large number now, or show you the results. So I have to make some assumptions. The noises should have mean zero, bounded variances, as well as the starting values, and my matrix should be summable. Okay, so it's quite plausible. Okay, so here comes the result. Under these assumptions, you can again find for every time point a constant independent of n, such that the mean square difference of the supremum between the two systems, the original one and the mean, is bounded by the sum of three rates. I will discuss these three rates now, okay? And of course, we're interested in conditions under which these rates go to zero. So of course, this result also holds if they don't go to zero, but then it's useless. Okay, so we're really interested in cases where these go to zero. Okay, so here they come, 1, 2, 3. The first one is a rate on the starting random variables. The second one is something on the connection between periphery and core. And the third one is something on the joint behavior of the periphery matrix and the correlation structure of the noise. I will now discuss each of them separately, okay? So let's start with the first rate. I will make a general assumption for it. So this general assumption will be useful for all three rates, so I will put it first. So I will assume that if you have your periphery matrix is typically with values which are quite small. So this is what it should be. And if you take the square and sum them up, this should go to zero. In McKean's example, this would be the case, because there you had no core, every party is somehow small. The rates are of type 1 over n, and if you do this, then you get 1 over square root of n, which is the rate I've shown you at the beginning. Okay, so this assumption I will need. Okay. Now, the first rate. For the first rate, it was a condition on the starting random variables. I will just assume that they are independent, or at least uncorrelated, as this is always the case if they are, for instance, deterministic. And if they are not independent, you just condition on the starting random variables and you have it. Okay, because I assume that the noises are independent of the starting random variables. So this is quite a plausible assumption, I would say. And in this case, the first rate just...
But this is not the case if they're deterministic. That's not what you want is that when you increase n, the initial values fulfill a large numbers. That's what you want.
Yes, this is this is the generalization of it. But if they are deterministic,
I don't know what that means.
if they are just so x naught is a fixed number, 0, for instance.
Okay, then you start from point mass at 0. That's what
Yeah,
you're saying.
or you can start from different points. So x1 starts from 0, x2 starts from 1, but not from a random variable. Because then, if you compute the covariances, I mean, if you have some deterministic number, so no random variables, it just be 0 unless you're on the diagonal. And then you have this rate is smaller than the one I've shown you on the previous slide, this squares, the sum of the squares of the periphery matrix. Okay? And of course, as Rama said, in general, it will be that the general condition will be that the starting random variables enter a large number. And if they're deterministic, it's of course the case. So there's, okay? So for the second rate, we need, well, I want to demonstrate it through an example first. Okay, so this example is the following. So you assume that you have a fixed set of core agents, NC many, it's the 2 here, and the number of periphery increases with n. Okay? Then I assume that there's no periphery to periphery action. It's just for simplicity. There can be something, but okay, so let's say it's 0. And on the other 2 blocks here, it's something of this order. They don't need to be homogeneous as they are here, but just it's this order. Okay, that's what's all about the order. Okay, then unfortunately, the second rate won't go to 0. Oops. Because, well, if you sum this up, then every product here will be 1 over nc times 1 over np, and you have exactly nc times np many, and this gives you 1. So that's bad. Okay. What do you need, really? What you really need is there are some zeros, yeah, which is plausible because you can think that a core bank will typically be not affected by too many small banks. You can have the zeros here, you can also have them here. I just put it here for simplicity, okay? The question is, how many zeros do you need? And the answer is, the number of entries, the number of non-zeros, should be of order strictly smaller than n. So maybe if n increases, you should only have like square root of n entries, for instance. Because then...
What's that block? What is the interaction of who with who?
So this block is the influence of periphery on core.
Okay, so... Yeah, but the thing is, since you do not say what you're trying to model, we don't really know if it's reasonable or not.
Well, it depends on what you want to model. So, for instance, if
I don't
you...
want to model. You want.
Yeah, I want to present a model that's
Yeah, but for example,
suitable for
is it-
many
is
different
it-
things.
Are you trying to model lending and borrowing? Are you trying to model something? I mean,
So, I mean, for instance, okay, if you take this lending and borrowing example, then this would mean how much money does a core bank receive from a small bank? From how many small banks does it receive money? And the assumption is here from not so many. So of order strictly smaller than n. Or if you have, for instance, a statistical model, so for instance, I know that people also use this in order to model default intensities. So if the default intensity of one agent increases, how does it affect the other one? If a periphery bank gets into trouble, this means it shouldn't affect the core bank too much. In other words said, the core bank shouldn't be interested in the behavior of a small bank. If it defaults, then it defaults. It does interest the core bank. So this is such kind of an assumption.
But if you look at the lending model, for example, you have a small number of core banks, then you have a large number of borrowers.
Mm-hmm.
That's the idea, right?
Yeah.
So the number of borrowers goes to infinity. So if a lot of borrowers default, this is going to have a consequence from the core banks.
Yes, of course. So what we are doing here is mean fill. Mean fill means the expectation. In extreme cases, it's of course very different. So mean fill says that the expected difference is small. But if a shock hits everybody, which is unlikely, then of course it can be very different.
No, but this is not the outcome, this is just the parameter of the model. So if the borrowers, if they have a lot of borrowers, they borrow from the core banks, I would expect that all the borrowers should be somewhere in this upper block, right?
So you mean that, for instance, the process is the number of cash you have, or the amount of cash you have, and then this block would be the cash the periphery gives to the core.
I mean, again, I don't know. It's your model, so you should tell us what you're trying to model. Is this borrowing or lending?
Not necessarily. So this model is really just about an interaction. What type of it depends on the concrete application. So I'm not familiar with the different types of applications, but I think that these interaction models, so for instance, if you just look at the statistical model, which does not explain the internal mechanism, but just only what you observe. So then typically you would observe that the large bank won't, this is my hypothesis, I don't know, but this is what I would think is plausible, that the big bank isn't statistically affected by too many small ones. Of course, if they all default, then you have a problem, because it's just the sum that goes over to the big one.
Yeah, but that's not what you're saying here. You're looking at the number of non-zero elements, not the size of each non-zero element.
Okay. Oh, I understand. Okay, so I should say, okay. By zero, I mean everything near to zero. Or strictly, so a zero can be something like 1 over n squared. It's also a zero for me. So I have, it's really about the order. So every zero can be replaced by something really small.
So here the zero in the first row does not, you mean that does not necessarily implies that the second periphery bank has no connection with the first core bank?
Yeah, just a very, very small.
Okay.
Yeah, just a very, very small. Because
But that doesn't happen in a model with identical agents. That only happens if you have heterogeneity.
yeah, but you do have heterogeneity here.
Yeah, but inside the block, there is no heterogeneity. You're assuming that all the periphery banks are identical
No,
in size.
no. So okay, I should say it again. So I put here. So I should replace. Okay. I should say it like this. So in this talk, when I write, I think it will switch, okay, yeah. So if I write 1 over np, I mean some constant which may depend on the p, on the bank divided by n over np. And I'm not interested in Cij. This should be summable, something like this, but they can vary. And also, if 0, I don't mean 0, but something really smaller than 1 over np. Yeah, so there can be something. Of course, it will affect the rate of convergence you have, because if you have instead of a 0 a small number, it will increase your rate by a function of this small number. So it's just the idea. So, or you have to think of it as the order. The order matters.
Okay, so let me ask another question. So it's simpler. So if this matrix is not invariant by permutation of the indices in the periphery, then you lose exchangeability, no?
Yes.
So that's not a problem?
No. Okay. So as I have said, this. Okay, I go back to the. So here, okay. This result holds even if the rates are 1 million. It's just useless, but it holds.
No, but that's not my question. My question is, you started from the Makin example.
Yeah.
In the Makin example, you need to describe the behavior of a typical particle and the distribution of the state of the other particles.
Yeah.
And the reason you can reduce the n-dimensional system to one typical particle and the distribution is that they're exchangeable.
Yes, but this you won't need here, because the reason here is really that it's this order will do this job. So for in the proof, I don't need to look at exchangeability at all. So that's really something we explicitly want. So we do assume heterogeneity, or want to incorporate it. So the periphery can, of course, be homogeneous, but is typically not. In the same way, the core can be homogeneous, but is typically not.
But can you have like the upper right block with identical entries, but it goes to 0 sufficiently fast? Is this?
Yes. So yeah, it's exactly like this. So okay.
So
it's very
the
simple,
entries
actually.
Go to 0 with small o and p.
So what the rate? I forgot the number. So maybe I think it's 2. Okay. So what you have is a I j a jk. This is from the periphery, and this is from the core. Maybe no, it's like this. Sorry. Okay, this over all j and k. Say up to capital N. It can be infinity, okay, but say it's capital N. You want this to be small. I mean, in reality, it won't go to 0 because you have a fixed system. So this is a fixed number, but you hope that this number is small. In this sense, what you really have to care about is the order and not if a 0 is a 0 or it's 0.0001, because then it will, of course, increase the rate, but it shouldn't increase it too much. Yeah, so that's really the idea. Okay, now you want this to be small. How can it happen? Okay, you have here NP times NC many pairs. Okay? If both are of order, again, I speak of order, this is 1 over NC and this is over NP, then it won't work, because then it's just 1. So you need them really to be, so each pair really to be much smaller than this.
So if either of them is small o,
then it works, yeah. So this was an example what I bring, but the general criteria is, of course, that this goes to 0. And this happens, for instance, if one entry is 0, then it kills one, or it's near to 0, then it nearly kills one. But you see, it's continuous. So it's not really whether it's 0 or 0.1. It doesn't really matter. So it's just the order. Okay. Good. Oops. Did I kill the microphone? No. Okay. So now I think we have understood the second rate. Third rate is something mixed. So okay, for a third rate, you have to look at the periphery matrix and the correlation structure. So there are basically 3 possibilities. There are, of course, infinitely many possibilities, but there are something in between these 3. Okay, so I will study the typical 3 possibilities. You can have that this rate goes to 0. The first one is the McKean assumption independence. Then the covariances will kill the entries, and you get it goes to 0. Okay, fine. Second example, which is just a small generalization of this, is that you have correlation but weak correlation. Okay, look at this. So this is the same matrix again. Yeah, these don't need to be homogeneous, and 0 does not need to be 0 but small. What is interesting is the correlation here. So again, so this is the correlation of the noises of the cores of periphery and the core and periphery. What the noises of the cores do, I'm not interested in. They can be as they are. Okay, so everything possible. It's really that the noises of the periphery, that they somehow should only be weakly correlated. Meaning, if you have 2 small agents, the individual noises shouldn't be too correlated, which is also a plausible assumption, I think. Okay? So they can be correlated to the noise of the big one, but among each other, they shouldn't be too correlated. Okay? Again, it's a thing about order. So the number of zeros you need here is that, okay, so you have here np squared possibilities, and the number of zeros or small entries should be of size strictly smaller than n squared. Then you again get that this goes to 0. Okay? If you track this rate back to the correlation. You can do this also by assuming that the correlation is arbitrary, but it's the matrix again, the interaction matrix here again, that it's sparse. And then you get the same thing, and everything is fine. Of course, these are assumptions, so you have to check, yeah, in applications. Okay, what I want to do now is I want to give you an example in the last minute I have, I think, where these assumptions I've made are satisfied. Okay, I will study a preferential attachment graph. So I assume that the interaction matrix I'm looking at is created a priori, before I look at the processes, a priori created by a random graph model, namely in this case by a preferential attachment model. So there are many variants of this preferential attachment model, but I will show this one. It may be not the best one, but it's the one where I have the result. Okay, so maybe we can extend it later on to other graphs. So I start with 2 vertices connected to each other by an edge in both directions. I put weights on the edges. You can choose any weight you want. Okay. How do I go from one graph to the other? Well, I create a new node and create a link between this new node and one of the old nodes. How do I choose one of the old nodes? Well, randomly, independently from everything else, and with probability proportional to their existing degree. That's why it's called preferential attachment. Okay, so nodes with many neighbors will likely have even more neighbors. Okay, the direction of, so I've chosen now the link. Which direction do you choose? Well, it's up to you. You can do what you want. Doesn't matter. What I want to do is I put a weight onto each linkage of order 1 over n. Okay, so this does not, okay, so this is one thing one has to think about. So it does not mean that if I start, I put 1/2 and then the next one is 1/3. It's not like this. It's really like, okay, you have n, you want to end up with n vertices, so you put everything 1 over n at the end. So it's not that they are different, okay? And I've one example here, so this is the 10 times 10. The core, they can be as they are. And here's what comes out as an example. And this would be this graph, actually. So this one. Yeah, so this is the core. And then I attach peripheries to it. And they have 1 over 10 here around. Okay? And okay, so that's how this graph is created. Why I'm showing this graph is the following. So I want to understand whether if I do something like this, a preferential attachment model, will this matrix I get after n steps satisfy the properties I've shown you before? And of course, yes, otherwise I won't show it. So the theorem I use is one by Maury from 2005. In such a model, the maximal degree is almost surely of order square root of 2. N, so n to the square root of n, sorry, square root of n. So this means that the number of periphery banks or agents that influence a core agent is really of order smaller than n, namely square root of n. Yeah, so if you create your matrix a priori by such a preferential attachment model, you will get the desired result. Of course, there are many things to do better. So for instance, you just don't start with 2 nodes. You can start with a fixed set of cores and then look what happens. There are many things you have still to do in this respect, okay? Just for the idea. I think I'm over time right now, so
You have a couple more minutes.
So what I want to do now is basically the same, just for nonlinear functionals. So I will just go to the idea. So everything the same, but no matrices anymore, but functional. So this functional maybe depend on the whole path of your processes. Of course, everything is fine, measurable, predictable, if necessarily locally bounded, everything. And most importantly, Lipschitz. Lipschitz, where the Lipschitz constant is described now by a matrix, which is the one I will use for the later on, of course. So this is what replaces the matrix in the linear case. Okay, so that's the idea. What I want to show now is only the limit system. So the limit system is, of course, a little bit more complicated because you don't have a linear structure anymore. So I again decompose the interaction of particles to my particle I into 2 components. So somehow I don't prescribe how you do this. And I don't even have a suggestion, but suppose you can separate important actions and not so important actions. So it's A and C and A and P. These important interactions you keep there, okay? What you do for the non so important interactions, you average them out in this way, which is the following. So you're interested in I, so you look at the typical influence of the other ones on any path in this ith component you can think of. And so typical means the expectation. And then you plug in your actual path. Okay, so that's what you do. And the noise. Then you can get your mean field theorem, which is the same, with one small but important difference. So the rate we can take here is not the same as before. So before we had three rates, but we aren't able to prove the same, but we need this rate here, which is stronger than the other one. So if this goes to 0, in the previous example, all of them will go to 0. This is actually this sparseness of the periphery block, of the periphery and the core periphery block. Okay, so this is what, for instance, would hold in this preferential attachment model. The reason why we, for instance, cannot use independence of the noise as before is that the proof of the theorem goes through covariances. And as you know, covariances are typically bad to describe dependence in nonlinear cases. So we cannot reduce, or we cannot deal with the case with independent noises at the moment. So even if they're independent, it won't help much for the rate, which is something one still needs to improve, but okay. So, okay, I think I'm finished now. So what we still have to do is large deviations, maybe some regular variation and contagion analysis, and maybe you have further suggestions. Otherwise, I would thank you for your attention. Everything, yeah.
So, just to go back to the definitions, you had two departures from mean field. One is the core and periphery distinction. Yeah. And then the other is what we spent some time discussing. Putting in zeros. Yeah. Is a second departure from mean field. Yeah. Okay, so there's two.
So yeah, as you said, these are two separate things. So this distinction between core and periphery is up to the applier. So you will typically do this because you see the matrix and you see, aha, this is not so important, so you put 0 instead of the small number you see. Yeah, so this is your free choice.
But in the example you gave, I didn't see this.
In which example?
In the example you gave of the scale-free graph.
Yeah.
Well, there is no distinction, right? So the graph builds up. Initially, you don't say this is core, this is periphery.
Yeah, that's true.
Afterwards, you look at the graph and say, oh, this bank is highly connected. I'll call it core.
Yeah, exactly.
But,
exactly.
It's
not a priori.
Yeah, but if you go back to this model, I mean, $1 is $1. So if I'm exposed to you or to JP Morgan for the same amount, I don't see why I'm going to weigh it differently in my loss. Actually, it doesn't make sense to me. So
yes, so the choice of what is core for you,
it's size.
It's not necessarily size, but in your case, exposure.
Yeah,
if you're exposed to me with 10 and to JP Morgan by 1, then JP Morgan would be a periphery for you. Or because it's uninteresting. But I will be the core for you. So the definition of what is core and periphery may may depend on the agent. Of course, this preferential attachment model, it was not like this, but if you want to apply, you can make the definition of core and periphery dependent on the agent. Does this answer your question, or?
I don't know what Charlie's question was.
I don't know what my question was.
No, but I have a question because I think first, so this is not really mean field, right? Because you.
Yeah, so it's partial.
So I guess you shouldn't have mean field. But then the question is, so you cannot use the tools used for proving these asymptotics in the mean field case. It's different, right?
I mean, it depends on how you prove the mean field case, first of all. If you use exchangeability, then you can't do it here anymore.
But that's the main point in mean field theory, right?
Yeah, but as you can see, you can also do it differently. So, for instance, the exchangeability is a key point if you want that independent noises affect the rate. This is, for instance, a point we cannot have in the nonlinear case. In McKean's example, even if you have nonlinear functionals, independence of the noises will suffice. Here not, because you lose this exchangeability, and because in the limit model, the periphery are still dependent because they depend on the core. We have to use different methods, indeed. Yeah.
Right, we have a few minutes to change over.
Okay, thank you very much.
Let's thank Chris.